Hello everyone, in this video we'll be going through the NCEA Level 3 Complex Number past paper from 2025. Last year the cut score for excellence was 20 out of 24 for this paper. For each question, there are 5 parts, A, B, C, D, E, and parts A and B are achieve level questions, C and D are merit level questions, and part E is an excellence level question. We'll get through that in another video. Let's get on to question 1a first. For question 1a, we're asked, when the polynomial 3x to the 4 plus px cubed minus 4x plus 5 is divided by x minus 2, the remainder is 27. Find the value of p. So let's first write down the polynomial first. And there are two ways to approach this. You can either use polynomial long division, which is not preferred because that just takes way too long, or you can straight away sub in 2 for x, because if you think about it, if x minus 2 is a factor, then when we substitute 2 into x, the number that it spits out should be 0. Or another way of saying this is that if x minus 2 or x minus something, x minus 2 is a factor, then we can rewrite p of x as x minus 2 times another bracket, right? And when we sub in x equals 2 in this bracket, or as in like if we sub in x equals 2 in any both of these brackets, we'll get out 2 minus 2 times something, and this will equal to 0 because 0 times anything equals 0. So this is just to say that when you divide by x minus something, you can just straight away sub in this number into p of x. But in this case, it doesn't come out as 0, but instead it's 21 because there's a remainder. It doesn't fully divide. So we have p of 2 equals 3 times 2 to the 4 plus p times 8 minus 8 plus 5, and this equals 21. Now, this is now just a linear equation to solve. We have 48 plus 8p minus 5 plus minus 8 plus 5 equals 21, and we have 8p equals negative 24. Hence, p equals negative 3. And there you go. This will give you, this will give you a U mark. Very nice. Now let's look at part B. We have the equation x squared minus 6kx equals k squared, and we're trying to solve for x. Let's get it into a quadratic form first, where the right hand side equals 0, and we do this by taking away k squared from both sides. Now, we don't have enough information to factorize this bracket yet. Therefore, when we can't factorize and get the value of x, we used our trusty quadratic equation, which hopefully you guys all remember. It's x equals negative b plus or minus the square root of b squared minus 4ac over 2a. If you're confident with algebra, just sub in the value straight away. But if you're not, it's very good just to list out your a, b, and c values. In our case, we have a equals 1, b equals negative 6k, and c equals negative k squared. Now let's sub in. X equals negative of negative 6k, which is just 6k plus or minus the square root of negative 6k squared is the same as 6k squared minus 4 times 1 times negative k squared all over 2a. And this is just 6k plus or minus the square root of 36k squared plus 4k squared over 2a, which is 6k over 2, because a equals 0, so I can just say over 2, and over 2 is fine. So over 2, so I have 6k plus or minus the square root of 40k squared over 2, which is 6k plus or minus 2 root 10 times k over 2. Root 40 is k 2 root 10 because root 40 equals root 4 times 10, which is 2 times root 10. Okay, and now we just divide by 2. In both times we get not 6 but 3k plus or minus root 10k. Therefore, root 10k. So therefore, x equals 3 plus or minus root 10k. Therefore, x equals 3 plus root 10. Should be a square root 3 plus root 10k, or 3 minus root 10k. And this should be it, which gives you another U mark. Very nice. Now let's look at part C. This is a merit level question, but let's just carefully read through the question first. We got to prove that the equation has real roots for all real values of k, where k doesn't equal to 0. Let's first rewrite this equation down and obviously expand the left-hand side by squaring both terms. And now let's put this equation into a quadratic form, which is k squared x squared plus x over k minus 3 equals 0, if this makes sense. And then for this term, x over k, we can write it as 1 over k times x minus 3 equals 0. That's just easy to spot. Now it's asking for to prove that the equation has real roots. So communication is key in the exam with the marker. So we have for real roots, the discriminant must be greater than 0, because we got to determine whether it has real roots or not, and we use the discriminant for it. Discriminant equals b squared minus 4ac. So b squared minus 4ac must be greater than 0. I'm just gonna substitute the values in straight away, but if you guys need to list out list out a, b, and c values, do that because it should be helpful. So I have 1 over k squared minus 4 times k squared times negative 3 should be greater than 0. 1 over k squared plus 12k squared is greater than 0. 1 plus 12k to the 4 should be greater than 0. Do this step by multiplying k squared throughout the left and right hand side. Now I have 12k to the 4 greater than negative 1. We'll go up here. K to the 4 should be greater than negative 1 over 12. And now we just need to prove that k to the 4 is greater than negative 1 over 12. So we can say, I'll say it here first. For all real values of k, so positive and negative values of k, and k doesn't equal to 0, k squared must be positive, right? Because if k is negative, k squared is positive. If k is positive, k squared will also be positive. So you can say for k is part of the real, k squared is always greater than 0. Since k to the 4 equals k squared again, therefore k to the 4 will always be greater than 0. Therefore, k to the 4 will always be greater than negative 1 over 12. Hence, the equation has real roots for when k is part of the reals. Therefore solved. And for this question, let's see the marking scheme. You get one U mark. You get your U mark when you reach this step. Here, this step. And you get your merit mark, which is your R mark, you get 1 plus, where is it? Oh, really? Wait, no. Oh, you get R mark when you explain this correctly over here. Right. Now let's get on to part D. This is our first complex numbers question, and we are required to use polar form. So the question asks, solve the equation z cubed plus 8m to the 27i equals 0, where m is a positive real constant. Write your solution in polar form in terms of m. Let's rewrite the equation first. Z cubed plus 8m to the 27i equals 0. So z is a complex number, if you don't know, and m is a positive real constant. Write your solution in polar form. Well, we're finding z, so let's get z onto one side and everything else to the other side. Now we're going to let z equals r cis theta. This is our polar form. And it's always good just to draw a graph first. It doesn't have to be good. I'll draw not a unit circle, but a circle centered at the origin. And now we have to take a look. So z equals r cis theta. So r cis theta cubed equals negative 8 m27i. So r cubed cis 3 theta equals negative 8 m27i. I get this by using the De Moivre's theorem. Refer to the formula sheet for that. When we have this, r is always a positive number, and r is always a positive real number. So therefore, r cubed or r to the anything cannot be negative. So hence we say r cubed equals 8m to the 27, and cis 3 theta equals negative I. Because r is our radius, it cannot be complex and it cannot be negative. So therefore we take all the non-complex, non-negative numbers for r cubed, and then the rest, the complex and the negative goes to the cis. This side is obvious because we have r cubed equals 8m27. So r equals the cube root of 8m27 should be very easy at this rate, which is 2m to the 9, because 27 over 3 is 9. Right, we have cis 3 theta equals negative I. Therefore, you have to take a look. Let's expand this first. Cis is cos plus I sine. So cos 3 theta plus I sine 3 theta equals 0 minus I. So I can say cos 3 theta equals 0, and I sine 3 theta equals negative I. So 3 theta equals cos inverse of 0, which is 1. So theta equals, no. Cos inverse of 0 is not 1, my bad. Cos of 0 is 1. Cos inverse of 0 should be pi on 2. So, or negative pi on 2. Doesn't matter. We don't know that. Plus or minus pi on 2. So theta is plus or minus pi on 6. I have, on this side we have I sine 3 theta equals negative I. So sine 3 theta should be negative 1, dividing by both sides. So 3 theta equals sine inverse of negative 1, which is, 1 second, pi on 2 pi, 3 pi on 2, could be negative pi on 2. So it can be 3 pi on 2 or So 3 theta can be pi on 2 or negative pi on 2. It's likely to be negative pi on 2, or we'll just take one value first. Just take the common value between the two. So both can be negative pi on 2. So theta equals negative pi on 6. So I can say theta equals negative pi on 6. Alright, it's taking a lot of pages. Alright, let's forget about the graph first. And let's bring us up to the top. So we have r cis theta equals 2m9 cis negative pi on 6. Therefore, and for our complex solutions, remember it's spaced out evenly across the circle. So we have a root here at angle of negative pi on 6. Let's zoom in a bit for that. We have an angle here for negative pi on 6. By the conjugate root theorem, we should have another root here. And then the third root goes here. So this is our 3 roots, and we have to find the angles for that. The angle for this is quite easy. It's just pi on 2 or 90 degrees. And this angle should be pi plus pi on 6. Or if we can't go over pi, we can say this: if this is negative pi on 6, this must be negative 5 pi on 6, or negative pi minus negative pi on 6. So this angle is negative 5 pi on 6. Therefore, we'll move this diagram on top first, so it doesn't block our working space. So therefore we can say theta equals negative pi on 6, pi on 2, and negative 5 pi on 6. Therefore, we have 3 roots by the fundamental theory of algebra, because we have the highest order of z is 3, so we have 3 roots. So I have z1, the first root is 2m to the 9 cis negative pi on 6. z2 is 2m to the 9 cis negative 5 pi on 6 and 6. And the third root, z cubed, equals 2m9 cis pi on 2. And therefore this is our 3 roots. Let's take a look at the marking scheme to look at where our marks are. Right. First mark is one correct solution. Let's check if all my solutions are correct. Yes, they are correct. So one solution correct is 1 U mark. All 3 correct solutions with justification. Well, didn't have any justifications in words in this in the answer scheme. So what I'm guessing is that it's just clear working from the start to the finish. So this will so getting all 3 solutions will with clear enough working, not as detailed as mine. You don't need to go in this detail. You get the merit mark or the R mark. Alright, this video has been going for quite a bit, so I'm gonna split this video probably in 3 parts. We'll go through the E question first, which is probably what most people is wanting. For our excellence question, it's testing our locus. The locus of a complex number z is described by z minus 5i minus z plus 5i equals 4. Find the Cartesian equation of the locus of z. Give your answer in the form ay squared minus bx squared plus k equals k, where a, b, k are constants. Funny thing about this question, I left it till last because I went on a very wild chase in the draw me into a very deep rabbit hole. So it's quite a tough excellence question to work with. But let's take a look. First, we do one Cartesian equation. So let's better get our z equals x plus iy. Now, subbing in z in this, we have x plus iy minus 5i. This is a very bad I. Minus x plus iy plus 5i equals 4, the modulus of both, if I missed. Now, what can we do? For me, in the first run, I just put it into the modulus equation and square rooted both of these. But that was a very bad idea. Instead, first of all, let's quickly do x squared plus y minus 5 I. No, not x squared. My bad. We have x plus y minus 5i minus x plus y plus 5i equals 4. And now, instead of square rooting right now, we have, and then squaring both sides to try to get rid of the square roots. What's a better way is to move one of the modulus to the other side. So 4 plus square root of x squared plus 5 plus y plus 5 squared. How I went from this step to this step is first, first getting this part into this side, and then for each of these modulus, I just put it into the modulus equation on your formula sheet, which reads modulus of z equals square root of x squared plus y squared. Hopefully you guys know what to do for this one. And now, putting into this form, it makes up way easier. We'll just quickly square both right hand side and left hand side. Squaring the left hand side, we get x squared plus y minus 5 squared equals, squaring the left hand side, we have 16 plus x squared plus y plus 5 squared plus 8 times the square root of x squared plus y plus 5 squared. If you're not confident with what was going on, I'll put brackets around this so you'll see better. We have 4, essentially we're squaring this side, and we do this by just your normal expansions, which is 4 times 4, which is 16, and then this whole thing times itself, which is that squared, which you remove the square root, and then you have this term times this term, and you double it, which is 4 times 2, which is 8, times the square root of x squared plus y plus 5 squared. Hopefully this doesn't sound too hard. If it does, it might not be a particularly good thing. Right, let's move on. We'll now expand both sides even more. Expand these brackets out. We have x squared plus y squared minus 10y plus 25 equals 16 plus x squared plus y squared plus 10y plus 25 plus 8 times this square root thing. Now we'll start canceling out terms, and now it's very good just to switch colors. If you have another pen color in the exam, very helpful. X squared, positive x squared, positive y squared, positive x, positive y, these can go. And then we have 25, 25, these two can go as well. Now we're left with, we'll move this 10y to the other side and this 16 to the other side as well. Therefore, we have negative 10y minus another 10y is negative 20y minus the 16 equals 8 square root of x squared plus y plus 5 squared. Now, we're trying to get rid of this square root, so we square both sides now. Therefore, we have, we can pull out a negative from both terms, so we have 20y plus 16 squared equals 64 times x squared plus y plus 5 squared, just by squaring both sides. And this will give us 400y squared plus 640y plus 256 equals 64 times x squared plus y squared plus 10y plus 25, which gives us, let's multiply out the right hand side, which is just copying the left hand side, equals 64x squared plus 64y squared plus 640y plus 1600. And now, let's combine the like terms. We have got, let's switch pen colors first again. We have 640y here and 640y here, so these cancel out. Now just have 400y squared and 64y squared. Therefore, let's just move everything to the left hand side now and make the right hand side 0. We have 400 minus 64, which is 336y squared. The y's go. We minus 64x squared, and we have 256 minus 1600, which is negative 1344. 1344 equals 0. And now we could do 336y squared minus 64x squared equals 1344, because if we go back to the beginning, we're required to answer define the Cartesian of the equation of the locus z, giving you an answer in the form of this form: ay squared minus bx squared equals k, where a, b, k are constants. So I have ay squared minus bx squared equals k. So we're in this form already. And for our last step, it's always good just to reassure, to write your thing down. So we have a, b, and k are constants. So we have a equals 336, b equals 64, and k equals 1344, and hence solved. This is a long and vigorous question. I personally didn't enjoy this question a lot. I spent too much time on it, but hopefully this video will help you visualize a bit more for this question. Thank you for watching.